thank you everyone for attending. We are going to be speaking today about the operationalizing of machine learning and deep learning, and specifically, I mean, the problem in general, as well as specifically how we address the problem for Spark and TensorFlow. And so what we'll do in this talk is we'll talk about the problem, and then we will discuss some of the solutions approaches, as well as we'll do a demo. So first of all, let's talk about the problem for a little bit. So I think, most people are kind of aware of the degree to which, AI and experimentation in AI has, permeated the marketplace in the last several years. And the fundamental issue that we are going to discuss today is essentially the deployment of this at scale and the ability to bring experimentation in AI into production reality so that it can actually affect the ROI of the business that's trying to benefit from it. So what you're seeing here is a data point on this issue, and this was a survey done by the McKinsey Global Institute last year. And what they basically said was that even though AI investments are growing rapidly, very few of them are really deployed at scale. And so what they found out when talking to about 3,000 executives at various industries on AI experimentation is a lot of people are developing, experimenting, contemplating it, but only a relatively small fraction have been able to make the leap so far into production. And of these cases that were reviewed, a decent number of them, for a variety of reasons, were not able to yet move beyond the experimental stage. But the ones that did actually saw benefit, and they saw benefit not just in the technology, but also in the impact it had to their bottom line of their business. So this is fundamentally the problem that we're talking about today. So in this webinar, what we'll do is take that kind of conceptual problem, and we'll break it down into what are the things that make operationalization of machine learning difficult. The approach that we at ParallelM have taken to this problem and the solution that we have developed, and then we will also show you a demo of a couple of different scenarios that can occur in operationalization of machine learning, and how we address them. So the first thing is there are a number of different things that make machine learning challenging in production that are different from the way that other complex applications are challenging in production. So every complex application is challenging to do in production, but machine learning has some unique characteristics to it. So one of them is the data set dependency. So machine learning, and by the way, everything I say about machine learning applies to deep learning. And there are specific differences in the productionization that we can discuss, but to a broad extent, the problems apply to both of them. The first is that it's got essentially, even though machine learning is code and it is technically reproducible, because the output behavior is so dependent on the input data set and how that input data set may or may not have been similar to what the model was trained on, it's practically speaking rather difficult to reproduce and understand what happened and identify good behavior from bad behavior in production. So particularly the fact that, even though it's code that typically implements an algorithm, and therefore even reading the code doesn't really help you fully understand what it does. So this is one of the issues. So to help you kind of illustrate to you the impact of an issue like this is just an example. And it's an example that may not be similar to what you're doing, but it's quite indicative of the kind of problem. So what you see here is a simple experiment on a public data set that measures, that attempts to predict SLA violations for video traffic. And what you see here in the table is essentially, the first table shows 4 different load scenarios. And these load scenarios are different, think about as different usage patterns. And the algorithm, which is in this case a very popular classic machine learning technique called support vector machines, is trying to accurately predict SLA violations. So what you see is that given the training set, which had labels in it, 2 different implementations of this algorithm both actually do very well in predicting SLA violations. So the first one gets accuracies of 0.84 to 0.99. Second one gets accuracies from 0.86 to 0.99, and so forth. So everything is going well. Now, what you see in the second table is what happens if you take either of these algorithms and you subject it in production to the other data set, a data set that was different, a different kind of load pattern than what it was trained on. And now you can see that the accuracies are basically all over the place. And the reason we know they're all over the place is because we artificially obviously know what the right behavior should be because we had a data set. But you can see from the second table that now, depending on the, how different the training data was from the, testing data, the accuracy could be, everywhere. And it also could be different depending on what implementation of the same general technique was used. So because of that, and how this manifests in production is that obviously what happens in production has no label, so you can't immediately tell that it's not doing well. But if the data set shifts, for example, and it becomes unlike what you trained on, then you could have a perfectly healthy running process, with no notable errors or resource issues or crashes or anything like that, generating subpar predictions. So this is a simple example of the kind of problems that occur in production. Another simple problem that occurs in production is how easy it is to actually end up with fairly complex topologies, even when trying to do simple things. So to illustrate this problem, first thing you can say is, so the goal of most people who are trying to put machine learning into production is to really do some kind of prediction in the aid of a business application. So this prediction could be something like, a user comes in, I want to know more about this user so I can recommend something to them, so on and so forth. And so the way you usually think about it is business logic has something it wants to do, reaches out to a machine learning pipeline, it provides some kind of prediction. So that's the thing that's really trying to be accomplished. Now, practically speaking, there are some industries where this pipeline can be put into production and you never change the model. But realistically, as environments change and as your data sets improve and you start getting more information, you may want to update new models. So at the very least, you need to be able to manually update the models that go into this inference pipeline. So next step is that, so now I need to update my model. Next step is that maybe I need to update my model regularly. So regularly, depending on the industry, could be anything from quarterly to weekly to, in some cases, which are very, very adaptive, could be even, multiple times during a day. So the next thing you want is you have to be able to retrain in production and you have to be able to update the model. So now your, machine learning kind of application now has two pipelines in it and they're running at different schedules. Next, in order to, have accountability for what occurred, you probably want these updates to occur with some kind of intervention or approval, or at the very least, some sort of authorization. This is very popular in environments where you either have, regulatory concerns or, the application itself has significant impact on revenue or health or some other kind of consequence. Then you now have this notion that in between the model updates, there's some sort of a human event or some policy that needs to be involved. So now if you assume that you had to do all of those things, but you wanted to use, like, say, a very, very common technique in machine learning called ensembles, where you actually allow multiple models to vote on the outcome. So now what you have is you have multiple models and they are probably training and you need to train them periodically as well. And then you combine them and drive that into the inference. So now you have a slightly more complex topology going on. Another factor that happens very frequently in production is the notion of a control pipeline. So the idea of a control pipeline is something where you can compare the behavior of two different models in production, whether to do an A/B test or to try to see if your primary algorithm is behaving erratically. So in that case, you may want to insert a control pipeline into the mix. So you can see now that every step that we took here is very logical and very straightforward and didn't really utilize any advanced machine learning techniques, but has resulted in a topology that's substantially more involved than the one that we started out with. So this is also another case of difficulty where what looks like a single pipeline might actually turn out to be multiple cooperating pipelines. The next part, and so this is one of the things that that makes machine learning challenging in production. And these multiple pipelines could be loosely coupled. They might involve human interdependencies in order to make sure that inference occurs as expected. The feature engineering that occurred for training has to be replicated for inference, and so forth. So these are some of the other things that make issues like orchestration and continuous integration in machine learning have just unique steps that need to be taken. The next thing that makes machine learning challenging in production is heterogeneity and scale. So because of the wealth of open source development that has occurred in machine learning, there are a number of very powerful engines out there that can run machine learning programs. So a quick list of them here, Spark, TensorFlow, PyTorch, and so forth. Multiple languages are used, and it's very common for inference to be done in a different architecture and possibly even a different language than training, because training can be frequently batch, and inference could be like a REST based element by element computation or some kind of a micro batch and things like that. And so in order to benefit from the technologies that are out there and the algorithms that are out there, you frequently have to put into production a heterogeneous combination of at least two different kinds of engines. And then you have to understand how to scale them and manage them to work with each other, as well as to meet the performance and volume needs of your predictions and your business apps. So this is itself presents a series of system-related production issues. The next one is the notion of compliance and the regulatory aspects that impact machine learning. So many of these are very industry specific. And so what I did here is I listed 3 examples that may not apply to necessarily your industry, but give you an indication of how the different industries are approaching and finding ways in which they need to understand the behavior of machine learning as specific to their industry. So in financial services, regulations have been around for quite some time. This is a pointer to one that has existed for many years that involves model risk management. Across the European Union, there, the GDPR regulations have certain statements in them that describe the need to be able to reproduce and explain various decisions of ML algorithms as they affect human beings. The third one is just another example of more of a local regulation, which is something that came out in New York late last year, where they established a commission to monitor the fairness of algorithms being used in day-to-day resource allocation in various types of government agencies. And so what you see here is that what you see here are basically various types of spot examples of different industries and different communities trying to figure out how to understand how these algorithms that are now impacting their kind of day-to-day decisions, how to regulate them and try to understand how they behave and how they should behave. The other point that this brings up, which I think is interesting, is that these regulatory requirements are not limited to cases of extreme financial risk or extreme life-threatening predictions. The last one, for example, is fairly routine stuff. It's about how budgets are allocated between government agencies. And so the need to regulate is not limited to a small corner of machine learning where people's lives are at risk. But it appears to be in lots of places. So this presents a practical challenge for operationalization in business, because in order to manage risk, you need to understand that the variety of different machine learning applications running and assisting your business logic are meeting whatever is considered to be the regulatory needs of your industry and your company. Finally, machine learning presents a people challenge that in many ways is similar to other kinds of people challenges that have occurred with advanced apps. And one of them is related to the mismatch in expertise between data science and operations. So data scientists are experts in the algorithms, the behavioral characteristics of them, the code, the error conditions, and so forth. But ops is, experts in other areas like resource management, upgrade mechanisms, and so forth. And typically bringing machine learning into production requires that both of these groups collaborate. And the very large difference in expertise can make it difficult for them to work together effectively. The final other thing is that machine learning pipelines are in fact code, and so a software development lifecycle that exists in for code is also part of bringing machine learning to production. But software development lifecycles don't really address the unique kinds of issues that that we discussed earlier in terms of how these applications actually run. So you need to basically be able to accommodate these things effectively to make sure that your organization can kind of run seamlessly and bring these things into production, but also continue to improve them and keep them healthy while they're in production. So what we are going to discuss today is, so the ParallelM approach to this problem, which is fundamentally, a full life cycle for machine learning applications in production. And so what we see is really, it's not a one-time, throw over a wall where you create an algorithm and then you throw it over into operations and then, don't worry about it again. But you have to actively be able to repeatedly develop these things, put them into production, be able to monitor and diagnose them when they're in production, collaborate between people in the data scientist side with people in the operations side, do continuous optimization, understand what happened in production, make sure the next release improves upon it, and so forth. And so what we see is that, and this is, by the way, the same kind of cycle that exists in any other type of advanced application. And what we see and address are the unique issues that are required to make this cycle effective in the machine learning world. So the product that we will show you today is called MLOps, and essentially focuses on a number of different functional areas. Going from the top left hand and going clockwise, it performs continuous integration and continuous deployment, which is really about making sure that updates and scheduling and new rollouts of algorithms and code and engines and so forth can happen seamlessly and correctly. Orchestration, which is what we talked about earlier when we talked about the need for dependent pipelines and understanding their relationships, and making sure that all those get executed with the dependencies intact. Health is some of the unique issues that come across when you try to diagnose the behavior of these algorithms in production, which is complementary to the behavior of the processes or containers that they run in. Both are needed. And when we talk about ML health, we're talking about the algorithmic behavior. Business impact is understanding how this is related to the business, how has it affected long-term KPIs, what is the relationship between the resource investment that has been made in machine learning to the net business benefit that has been achieved on it, things like that. And finally, governance, which reflects, understanding, how these models are being deployed, what is their lineage and provenance, and making sure that those in turn can be validated and subjected to compliance reviews and other ways of making sure that the regulations of the industry and the organization are met. And this is, of course, wrapped in the collaborative element so that all the suitable stakeholders, whether they be data scientists, data engineers, IT operations, or possibly business folks, can collaborate as needed to make sure that these pieces work. So the approach that we take architecturally is described on this in this slide. So what you see here are the blue components, are the components provided by ParallelM, and the other components are those that exist frequently in typical data center environments that are implementing machine learning or have other kinds of data engineering practices within them. So very frequently, many types of analytic engines are used, and there's some examples here. We will discuss specifically Spark today, and we'll also talk a little bit about TensorFlow. There are, of course, many kinds of data lakes, whether they be HDFS or databases or key value stores that are used to keep the actual data. And then there are a number of development environments that data scientists might be using to originally develop these algorithms. So what the MLOps product does is it works collaboratively with these various entities via an agent server architecture. The agents connect to the analytic engines themselves and operate in the control path. And so the control path implies that we essentially get involved in the launching of pipelines and the monitoring of the behavior of those pipelines as they run. The agents communicate with the server, which executes the various functionalities that were listed in the previous slide. And then the different users of the system can interact with the system either actually through a user interface or in an automated manner through kind of a REST interface and operate all the different things that they would like to do to manage it. And you'll see some of that in the demo as well. So with this approach, a number of things are, the approach itself helps us address a number of the issues that we saw in the previous slides. One of them is the heterogeneity and scale. So under this model, people can use any engine that they like, and they can also use any combination of engines that they like. And so because of that, all the different applications that are being made available in the open source community, new algorithms, new feature engineering functions, all of those can be leveraged in production because we work collaboratively with these engines. Same is true for data, data lakes and stream brokers and so forth. So the massive heterogeneity in that space is cleanly accommodated. Given the agent server architecture, also and the fact that the MLOps server operates in the control path, a large amount of data processing can occur between the data lakes and the engines, and with the agent and server consuming a very small amount of resource because the data doesn't flow through them. So these are some of the elements of basically the architecture and how it operates, and you'll see some of that during the demo as well. So just a very quick note on how to think about MLOps relative to DevOps and the software development lifecycle. So, and this is a graphic that kind of helps explain how we at least think about MLOps and what's needed there, and explain that MLOps is intended to be collaborative and complementary to DevOps particularly. So fundamentally, since machine learning algorithms are code, the code has typically a software development lifecycle attached to it and may live in a source control repository like Git, and may get deployed through standard DevOps practices. So where those occur, we believe that it's important to be complementary to those. So as an example, if an environment that may actually have its own source control mechanism, for example, is something that we link to. Similarly, when it comes to areas of automation and scale, and for example, provisioning of hardware resources, the MLOps stack actually works collaboratively with resource managers like Yarn to make sure that whatever is being done in the environment, can be done pretty much the same way it was done before. The places where we really focus are the places where machine learning unique application management becomes necessary, and standard DevOps does not address that problem because that is not its intent to address that problem. And that comes into areas like compliance and governance, risk management, business metrics, and the overall management of the machine learning pipelines regarding their ML behavior, not necessarily regarding their resource management behavior and so forth. So the way that we do this fundamentally is that we enable customers to create operational abstractions that tell us how their machine learning pipelines are related. And we call these abstractions ions. But basically, they are graphs that allow you to specify the different pipelines that you intend to run, what is their behavior, how are they related to each other, how are they related to human actions that may be needed, and then map these to various types of execution environments. And in doing so, we can basically allow you to manage your machine learning as applications that then in turn map to different kinds of engines like Spark or TensorFlow and so forth. And here's a simple example of such an entity. And you can see that what this shows you is essentially two pipelines. And these two pipelines, the first one on the left is doing training, and it's doing training in batch on Spark. And the output of that, in this case, because it's a k-means batch training, is a series of centroids. And those centroids are provided to a streaming engine that can, for example, handle live streaming data from something like an IoT device and detect anomalies. So by describing a pattern of this nature, you can describe the end goal is the anomaly detection. But the algorithm that's doing the anomaly detection is being fed by a training pipeline. And so you can describe your entire environment, and these can be running in different geographical locations and different analytic engines, or even different languages. And, but it will still be managed at the application level. So just a few quick comments on how we integrate with different analytic engines. Spark specifically, the key thing to note about the integration with analytic engines is that the engines themselves are unmodified, which means that the customer can get the engines from the primary provider. You can get them from whatever open source distro is currently published it. We are also do not require that we take over the engine. So if depending on how the engine itself is deployed, you could use it in parallel to do other things like ETL, for example, and other pipelines that may not be necessarily managed through us. So in order to maintain this type of integration that does not change the engine, each of our agents speaks to each engine in the native APIs and interfaces that are available from it. So for Spark, for example, for job management and statistics and other things, we work with the native Spark utilities that are provided for these purposes. And our agent basically uses these native utilities to communicate with Spark. And we use the launch side to launch pipelines, and we use some of the listener capabilities and standard statistics gathering mechanisms available in Spark to monitor and absorb statistics. Similarly for TensorFlow, TensorFlow is structurally very different from Spark, but the approach that we take is the same in that our agent integrates with the engine in ways that are standard for that engine and in ways that do not modify the engine. So in the case of TensorFlow, for example, the programs run as standalone applications, and we are capable of launching them as such. And statistics collection occurs via standard TensorFlow tools, specifically TensorBoard. But above all of this, the other mechanisms that we provide for orchestration, CI/CD, governance, and health monitoring, for example, are standardized, which means that you can have applications that run across multiples of these engines. You can even have a single application that has different pipelines on different engines. And at the lower levels, all of that will be handled in engine-specific ways. At the higher levels, it's completely abstracted, and all the other mechanisms that you see will be practically the same. The specific statistics that you see are obviously specific to different algorithms, and deep learning, for example, has a series of statistics that are meaningful to it, and statistical machine learning, depending on the algorithm itself, will have yet other kinds of statistics. So what I'm going to do is to stop here, and we're going to go through a quick demo. The demo will focus on Spark, and we can answer also any questions right after the demo. And the key thing to note is that we'll show you a number of different scenarios with Spark that illustrate how the production lifecycle works. And due to lack of time, we'll obviously show you only a few things. We'll focus on some of the health management and some of the collaborative aspects between operations and data science. What we are showing you, virtually the same things are available for TensorFlow, but it's just that there would be TensorFlow programs that will be running. So what I'm going to do now is I'm going to stop sharing, and I'm going to switch over to my colleague who's going to show you a number of demonstration videos.
Cool. Hi, everyone. Now we've come to the most exciting part of the webinar, the demo. So here we want to show a couple of scenarios here. I'm going to particularly show 3 different scenarios that one can go through. So in the interest of time, I'm not going to talk about all of the product as Nisha mentioned. The first part basically is how do you meaningfully monitor and diagnose issues in production? So what we do is ions are synonymous to machine learning applications, which make sure that we can take in 1 or more pipelines together and then monitor them. Here we see that an administrator actually has logged in, and then he can get a knock view, and he sees that one of the ions actually has a bad ML health. And when he goes in, he clicks on the health, and then he goes to the health view, and he gets to see the aspects of how the system is currently running. So we also provide you a heat map that shows how the current data is changing in production, which means for the inference pipelines, and also for each attribute that are changing as compared to the training metric, we show different histograms too. So as an operator, he can quickly log in, he can see what is changing, he gets to see the heat map visually saying how it's changed, he gets to see the events that are there, and we show where the events actually track on the timeline of the heat map. And then as an operator, you don't really have to debug if you don't have all the machine learning expertise. An MLOps person simply can capture the state of the application. The cool thing about our state capture is we call as timelines, captures everything with respect to this application, which includes pipelines, the parameters, the statistics, the logs, all of them can be captured with a one click of a button. And then all an operator needs to do is simply go back to the previous model. If he knows that the new model is causing a problem, he can simply go back and say, I want to revert back to a previous model. And he can pick the pipeline that he wants to revert the model to. In this case, there's only one pipeline running. And simply say why he's reverting, because he's seeing too many health alerts. And as a result, once he does that, the system goes back to the state it was before the alerts are happening. So it takes a few seconds for the model to actually be moved from to the production pipeline, and then actually change the health status. So we'll wait for a couple of seconds. I'll quickly move through those in the interest of time. And you can see that the health status now has changed back to green. So as an operator trying to manage things, like it's very, very simple for them. All they have to do basically is check the status. And then if the status is bad, they can quickly take a snapshot or a timeline capture, and then they can revert back to the previous model. Now, and then he can send out an email for a data scientist. So a data scientist comes back, logs in next day morning, after the coffee, and then they log in, and then they have the action item given from their administrator. So they simply go to the timeline captures that administrator has already captured for them. This is in the context of the ION that we talked about for fraud prevention. And you can see the alert, the timeline capture that he has done, which is called as health alert. And you can see it was taken yesterday from 8:27 p.m. to 9:27 p.m. So he simply clicks on the action and then says browse. So what browse lets you do is to let the data scientist look at the system as if he's looking at live. And here you can see that this is a timeline view. And then he can look at different points in time where he can adjust the window of time that he wants to look at, see how the events have been changing, how the heat map has changed. And he can also go to his own view, which is the data science view, and check the statistics of each of the pipeline, the training pipeline, inference pipeline. In this case, what you can see here is that the change of the model is causing the prediction distance to change or creating a behavior that is causing the health alerts. So you can understand what happened at the time of the time that the health alert happened, and he can also go back and check the training metrics of the model that was used, and then see what was the training metrics and how did it differ from the previous training instances, and then he can try to do some more triaging and debugging. And the beauty of this is that we don't need a real-time debugging support for both operators and the machine learning data scientists. They can do it offline and then collaborate to solve problems in production. This is one scenario. We'll show another scenario again. Give me a second. So the second scenario, what we want to show basically is how do you meaningfully approve models into production so that you can deploy models in confidence, saying that it actually is going to help improve your system. So in this case, you can see that for running ions for an operator or a data scientist, you can see the list of models that are pending approval. So all they have to do is click on actions and click approved models. And then you can see the list of models that are currently pending approval. And for any model, you can perform a bunch of actions. The first action is to download the model, where you can take it in your own environment, do some additional testing or processing, verifying that it's working correctly. Or you can actually go and look at the exact statistics that the training statistics for the model that was generated. Here you can see the different statistics like distance matrix, prediction histogram and stuff. So as a data scientist and operator, you can make sure that you've gone through the due diligence step to make sure that how the model has been behaving. And then you can check for different models. And then you can also check this model with the previous other models that are pending approval, or also for that matter, the model that is currently running in production. So once you do this comparison, then you're happy with it, you can simply go back and then say you want to approve the model or reject the model. And for each approval rejection, we also capture the annotation saying, why do you approve this model, so that you can always track it for governance and auditing purposes. So this is the example how you can approve or reject a model before it actually put into production. Okay, and finally we'll see the third scenario, and similarly you can see for rejection also you can add the annotation as needed. And then we are going to show how do we actually deal with the third scenario, which is how do you actually build ions or pipelines and then put them together to solve a business problem. Okay. The third scenario, now from monitoring mode, we go back to the building mode. In the onboarding part, we have two parts. We have the components that are the building blocks of a pipeline. Small parts like the data ingestion, the feature engineering component, the algorithm component, or the sync components. We have all of them for different engines. And you have categorized according to the type of what they are for statistics, algorithm, source, sync, or feature engineering. Similarly, you can take these components and convert into a pipeline. So we list all the pipelines that is available. And then you can group these pipelines into an ion. In this example, you see the ion or the business application having two different entities like Nisha showed earlier. You have the first entity on the left, which is basically the training component. Okay, and then you can click on the pipeline and then you can see the details of what the pipeline consists. Here it consists of three aspects. One is the source component, feature engineering component, and algorithm component. For each component, if you click on it, it will give you the list of parameters that you need to provide and what is set for each of them. So that as a result, you can always go back and check how the particular business application was configured with its constituent pipelines, schedules, and where they are running and stuff. Okay. And similarly, we are showing for the inference pipeline, the prediction of the inference pipeline that we are using. It is running an anomaly detection pipeline, reading from the input source, which is basically Kafka, and performing and for each sample it checks whether it is an anomaly or not. And this is basically for fraud detection. And this and the simple arrow between the training and the inference part indicates that the model actually is going to be propagated from training to the prediction pipeline. And then you can also specify different schedules of how often do you want to run it, and also add policies that you want to provide. In this example, we say that the models should always be propagated from training to the inference pipeline, and you can have different health thresholds that you want to provide. In the interest of time, we will not cover the health thresholds, but you can also configure how you want to detect the healthiness of your business application. Okay, so this at a high level, what we saw in this third part is how do we group individual components into pipelines, and how do you put pipelines into a business application or ions, and how do we actually configure these pipelines actually to run together to solve a business problem. And then we can say, how do you set policies for this application? I think that covers the end of the demo section. I'll give it back to Nisha.
Sure. Thank you, Swami. So what we're going to do now is I'm going to start the Q&A session. And before that, I will try to, we're going to stop the recording and basically